Hi, thanks for joining me today. I've got a really cool inequality I want to show you, and this is adapted from a step question. So we have a function y of x, which is differentiable, and I perhaps should have mentioned it's also a real valued function, and it satisfies that y of 1 equals 0. We want to prove that the integral from 0 to 1 of y prime of x squared dx is always going to be at least the integral from 0 to 1 of y of x squared dx. And for a bonus, ask yourself, when does equality hold? So all I'm told about y is that it's a differentiable real valued function and it satisfies y of 1 equals 0. That's all I know about y, and it somehow appears to be that this inequality should always be true, regardless of what y of x is, provided it satisfies these few conditions up here. So if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive right into a solution. Okay, so our problem is in fact equivalent to showing that this integral here is at least 0. So this is the integral from 0 to 1 again of y prime squared minus y squared. So we've just kind of brought everything to one side. So we want to prove that this integral here is at least 0. So this is what we want to prove. So let's call this integral, give this a name. So I'm going to call it I1, because in theory this would be a number. And what I'm going to do, and here's the trick, is I'm going to introduce another integral, I2, and again it's going to be the integral from 0 to 1, but now it's going to be y prime plus y times tan of x squared dx. Okay, and so this is just something I've defined to be I2, and again I've omitted the x's here just for simplicity, and now what I'm going to do is consider I1 minus I2, so I1 minus I2. So what is I1 minus I2? Well, I can bring everything under one integral, which is nice. So it's just going to be the integral from 0 to 1. If I just write down what I1, the integrand of I1 is, it's y prime squared minus y squared. And then I'm subtracting off the integrand of I2, which is this thing, y prime plus y tan x all squared. So if I expand that out, I get a y prime, oopsie daisy, squared, plus 2y y prime tan x, which I'll just denote with a t for now, and then plus y squared tan squared x. All of this dx, like so. And now we get some nice cancellation. So the integral from 0 to 1, this y prime squared here cancels with this minus y prime squared. And then everything we're left with is in sort of minus. So we've got minus y squared t squared, which I can just write as minus y squared 1 plus t squared. And then minus 2y times y prime times t. Again, dx, like so. But now, remember, t is just tan x, and we've got 1 plus tan squared x, and hopefully if we know our trigonometric identities, that's just the same as secant squared. So I can write this as y minus y squared, and perhaps I'll add in the trigonometric functions now, minus 2y prime times tan x dx. And now what's really nice about this is I can actually just spot the antiderivative of this. If I have a play, if you've seen derivative problems before, you might know what the derivative of y squared is, and it's 2y prime. So we can actually just spot that the derivative, or the antiderivative of this, is just minus y squared tan x. Again, between 0 and 1. And just to double check this, if we differentiate this using the product rule, if we differentiate this first term first, so minus 2y times y prime times tan x, which is that term, and then if I keep this term and differentiate this, I get minus y squared sec squared x, which is that term there. So this is exactly the antiderivative, and again it's between 0 and 1, so if I plug in 1, I get minus y squared of 1 tan of 1, and then if I plug in 0, I'm going to get minus minus, so plus y squared of 0 times tan of 0. Tan of 0 is 0, so that term vanishes. And remember, in the problem we insisted that y evaluated at 1 was 0, so this term here also vanishes. So we get that this equals 0, which is really, really nice. So I1 minus I2 is 0. So that tells us that I1 equals I2. So if I1 equals I2, we have this integral here equals this integral here. But we can clearly see, because y is a real valued function, this integrand here is some real valued function, and we're squaring it. So in particular, it's going to be a non-negative function, and we're integrating it between 0 and 1. So this thing here is certainly going to be positive, and that tells us that I1 must be positive, or non-negative at least. So I1 equals I2. And since I2 is non-negative, it must follow that I1 is non-negative. And that solves our problem. Now let's have a quick look at the bonus problem. Okay, so now on to the bonus problem. We've just proved that I1 is at least 0, and we now want to know when is it equal to 0. So when does equality hold? We've proved that this integral here equals this integral here, so you can probably guess that we're going to do some stuff with this integral here, because the thing that's nice about this is we have that the integrand is a real number, or a real function, which is always non-negative, because it's something squared. So cool, we have, if we suppose this thing here equals 0, we want to know what's the value of y, what function can y be. So we know that we're integrating something that's non-negative between 0 and 1, and we're getting 0. It turns out that that must be that the integrand therefore must be constantly 0, so it must be exactly 0 regardless of what x is. And this kind of makes sense, you know, certainly if this inside here is a continuous function, if you think of a continuous function which is non-negative, if you're integrating it between two values and it equals 0, it must be that the function itself is exactly 0, because if it's not, if it's non-zero somewhere, let's say there, then, you know, because of continuity, it's got to be, you know, a little bit positive around it, and then even if it's 0 elsewhere, the integral of this is still going to be some small positive number. So that's kind of one way of convincing yourself that's true, but I guess one thing that we don't know is this function actually continuous? Because it could be that y is differentiable, but it's not continuously differentiable. But it still turns out that we actually need this thing here to be exactly 0, and to see a rigorous proof of this, I'll leave a link in the description below to a video I've made where I use kind of the Lebesgue measure definition of the integral to prove that if you have a non-negative function and its integral is 0, then it must be that the integrand itself is 0. So that's really technical, but anyway, I'll leave links to that in the description below. Let's carry on. We have that y prime plus y tan of x equals 0. So now we're just solving a simple differential equation, and this is a really nice first order one, so we can just say that dy dx equals minus y tan of x, and then kind of do the cheeky little trick, and I'll put this all in inverted commas, and say that, well, we have that 1 over y dy equals minus tan x dx, and then just integrate both sides. So on the left hand side I have ln of y, and on the right hand side I have minus log of sec x plus c, but I can just kind of put that plus c, absorb it into this thing here. So I've got, therefore y is just equal to a cosine of x by bringing this minus into the exponent and then getting rid of the logs. So y is equal to a times cosine of x, but remember we have to have the condition that y of 1 equals 0. So if y of 1 equals 0, we have that a times cos 1 is 0, and cosine of 1 is definitely not 0, so we can get rid of that, and we have that a equals 0. And if a is 0, that means that y is identically 0. So the only way we can have equality, in other words, the only time the integral from 0 to 1 of y prime squared equals the integral from 0 to 1 of y squared, is when y is the constant function y equals 0. And that solves the bonus part of the problem as well. Anyway, I hope you have enjoyed this video. It's a really cool inequality requiring very few conditions, and it's something I don't think I've seen much before. Can't really think of any uses of it, but I think it's quite neat that it should hold anyway, regardless of the function of y, provided it's differentiable and satisfies y of 1 equals 0. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.